Today we will try to understand what Pauli's exclusion principles says. Pauli was Wolfgang Pauli was an Austrian scientist in 1926 stated that no two electrons in an atom can have the same set of four quantum numbers, right? So what we are so because we are in the chapter atomic structure, chapter number 2, atomic structure of class 11. We are after learning the quantum mechanical model of an atom, means the quantum mechanics to explain the structure of the atom, where we find quantum numbers, or a full set of quantum numbers which characterizes every electron present in an atom, which is a natural consequence of solving the Schrodinger's wave equation, which considers that electrons behave like a wave and it has a wave function, which is a mathematical function, and these quantum numbers are the natural solution in solving the equation, Schrodinger's equation for every electron present in an atom. Right? There's four set of quantum numbers, as we have learned earlier, are the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the last but not the least, the spin quantum number, which has only two possible values, either plus half or minus half. Right? Pauli says that. So Pauli says there are no two electrons. So in this atom that I have drawn over here, it contains four electrons. So in the nucleus there are four protons, but I have not put any sign for the neutrons, which are neutral. It should be in the nucleus. So we're trying to find out what will be the four set of quantum numbers for each of the four electrons those are present here. But please remember that I have drawn a very simple diagram. The diagram of an electron is not that simple, because according to Heisenberg principle, we are not supposed to know the precise position and the velocity of an electron around the nucleus in an atom simultaneously. If we try to know, there will be uncertainty in the position and the velocity of an calculating. There will be uncertainty in calculating the position and the velocity of an electron in an atom, and because of that we are not able to say specifically that an electron will be present here at this moment. We only can say that the probability of finding an electron is highest over here, and those places are called orbitals. There are many shapes of the orbital: s orbital, p orbitals, d orbitals, f orbitals, g orbitals, h orbitals, which has been described by the quantum number L. Right? The energy is given by the quantum number n. But in multi-electron electrons, the energy is all value of L also contributes in an amount of energy an electron possesses. N plus L, the value of n plus L gives the amount of energy an electron would have, except for hydrogen-like atoms or hydrogen itself. So the Pauli says that no two electrons in an atom can have the same set of four quantum numbers, right? So let's try to find out these two electrons, right? These two electrons are in the first shell, 1s, and let's see what are the four set of quantum numbers for these two electrons. Since it is in the first shell, n equal to 1, the principal quantum number n equal to 1, it also signifies the energy. Since n equal to 1, the value of L, the azimuthal quantum number, there is only one possible value of L. It will be 0. Had it been n equal to 2, then there would be two possible values of L, 0 and 1. Had it been 3, n equal to 3, there will be three possible values of L, and it will be 0, 1, and 2. But since n equal to 1, there is only one possible value of L, and it will be 0. The value of L depends on L, right? Where 0 means it is in an s orbital. So this electron is in an s orbital, as in the first shell. So its subshell notation will be 1s. Now, if L equals to 0, what will be the value of magnetic quantum number, m? So you know that again, magnetic quantum, the value of m depends on the value of L. Since it is 0, its value will be 0. There's no orientation in it. So we are having three quantum numbers with this electron, and the fourth one, right? S will be either plus half, it can be minus half also. Now what about this electron, which is in the same shell, 1s? In the same shell, this is the first electron, this is the second electron, this will denote this. So for here also, since it is in the first shell, the value of n equal to 1, since n equal to 1, the only possible value of L is 0, that means it will be s orbital, and since L equals to 0, the possible value of magnetic quantum number m will also be 0. What about the fourth quantum number? Since this was first plus half, this will be minus half. There are only two possible values of of a spin quantum number. Spin quantum number, you can have an analogy with like planets, like the Earth revolves either from east on its axis, right, from east to west, or some other planet from west to east. So the way the electrons are spinning around its own axis, it's either clockwise or it's either anti-clockwise. It's denoted by plus half and minus half, right? So these two electrons, although the first three set of quantum numbers are same, they differ in the fourth quantum number. So that's what it says. No two electrons. These two electrons are supposed to have all the quantum numbers same, but we find that three of them are same, but the last one, the spin quantum number, are different. One is having plus half value, the other one is having minus half value. So the fourth set of quantum numbers, no two electrons in an atom can have the same set of four quantum numbers. So this has been explained over here. What about, let's consider some other electrons. So for example, this one. What about this one? These two have, since for this electron, since it is second shell n equal to 2, that means the first quantum number itself is different, right? So there is no point of looking at the other quantum numbers. It says that the four set quantum numbers should not be same. Here, for this four set, the first quantum number itself is different. There's no point of looking at this other quantum numbers because they are in second shell. And what about L equals L? A value of L depends on the value of n, but it can have 0, 1, 0 and 1. L will have two values, either 0 and 1. 0 means S, and if it is L, if it is 1, it will be dumbbell shape that I have not drawn over here. The magnetic quantum number, since this equals 0, m equals n will be 0, and spin quantum number may be plus half or minus half, whatever it is. But to these two electrons, the first quantum number itself is different. So the Pauli's exclusion principle, I think it's understandable. Now let's come to the second way of stating the Pauli's exclusion principle. It says that only two electrons may exist in the same orbital, and these two electrons must have opposite spins. Yes, opposite means one is having plus half and minus. This means that in this orbital, how many electrons it can have? Can it have 3 electrons? No. If it has 3 electrons, then these three quantum numbers are same. And what will spin quantum number? It can have, and I said it can have spin. I can have spin quantum number has only 2 possible, plus half and minus half. If one more electron is present here, it will have the same set of first 3 quantum numbers, and the fourth quantum number we don't have any option, would be same, either with plus half or minus half. So it will be equal to either this or equal to this. So it's not possible to adjust 3 electrons in one orbital. So an orbital will maximum contain 2 electrons, and those 2 electrons will differ in what? It will differ in their spin quantum number. Okay, let's try to understand here also. This is a diagram, and it's also represented like this. This is 1s orbital. This one, right? I'm drawing just a box, and inside this box, these are the 2 electrons. 1s. What are the 4 quantum numbers? See, for these 2 electrons, the first 3 quantum numbers will be this: n equal to 1, n equal to 0, m equal to 0, because it is in the first shell. N equal to 1, s means l equal to 0, and s is l equal to 0, m equal to 0. So these are 3 quantum for this electron. The 3 quantum numbers are this. What is the fourth quantum number? It will plus up. So let this be the upright arrow. Half arrow denotes plus up. And what about second one? It will n equal to 1. Since it is in the first shell, L equals to 0 because in S, so its value is, so it's S orbital. M equals to 0. It's only possible value of M. That means that orientation doesn't matter for S orbital, right? And what will be the spin quantum? It will be minus half. How is minus half written? It's upside down arrow, half arrow. So in this orbital, how many electrons can you keep? You can put only 2. You cannot put a third one, because if you put the third one, its quantum number, these 2 will be the same, these 3 will be the same, 1s, and fourth one, s, it will be either plus half or minus half. Whatever it is, it will be the same with the other electron. So in an orbital, there can be only, in an orbital, either 1s or 2s, there can be only two electrons possible, and those 2 electrons will have the opposite spin quantum number, 1 plus half and minus half. What about this one? in P, there are three orbitals: P, 2px, 2py, and 2pz, depending upon the value of m, right? Because the value of L equal to 1, so the value of possible values m are -1, 0, and +1, -1, 0, and +1 in 2p orbital. But in each orbital, here in these two orbitals, these two electrons, they have all the three quantum numbers same. It will not be this, it will be n equal to 2 and L equal to 0 or m equal to 0, like this. No, it will, L will not be equal to 0, it is L equal to 1 for this. P means L equal to 1, right? So L equal to 1, n equal to 2, L equal to, okay, let's try to write this. What is the value of n here? N will be equal to 2, this second shell. Since P means L equal to how much? L equal to 1. And what about magnetic quantum? Magnetic quantum number maybe +1 or -1 or 0, whatever it is. And what will be the spin quantum number? Similar, for this electron it will be +r, and for this electron it will be -r. So this is the way the four set of electrons can be known from the orbital where they exist. And in orbital, so these are three orbitals, right? 2px, 2p subshell, but in the subshell there are again three orbitals: 2px, 2py, 2pz. That depends on the value of m equal to +1, here m equal to 0, or here m equal to -1, whatever. It may change. So for three values of m, +1, 0, and -1. But in one orbital, the two electrons will have the same set of three quantum numbers, and the fourth quantum number will be different. It will be either +r or -r. And because of that, Pauli's exclusion principle says that in any orbital, only two electrons are possible, and those two electrons will have first three set of quantum numbers same, only spin quantum number will be different, will be opposite, +r and -r. Hope you are understanding this.